Welcome back, everyone. We're about ready to wrap up chapter 4 already. And I think this one's going to be fun. You might find these distributions a little bit similar, but a little bit different. I always enjoy doing this one though. So let's look at 2 more discrete probability distributions. They're not the only ones, but the only ones we're going to talk about. So we've already talked about probability distributions in general in the first section, binomial last time, and we'll pick up 2 more. Let's see. We're going to talk about the geometric distribution, and now if you know French, you might shoot me for pronouncing it this way, but I think it's the Poisson distribution. Anyway, that's what I'm going to call it until I learn better. Alright, so we're going to talk about these. Not very long. This is going to be a short lesson. The one thing you want to make sure you do is make sure that you don't get these 2 mixed up. So take a few good notes. You won't have to take much. Trust me, this is going to be short. It's a discrete one, just like the binomial is. And here are the conditions. You want to write these down. First of all, you're going to do something, a trial, until you get a success. For example, if you're familiar with basketball, what you might do is go to the free throw line and keep shooting until you finally get the ball in the basket. It doesn't sound like very fun, but maybe you'd have a game where the person who takes the least number of trials until they actually get the ball in the basket is the winner. Maybe something like that. Golf might be a good example too. And you're going to repeat the trials, but they're going to be independent of each other. So if you're a 60% shooter, then your probability on the first shot is 60%, the second shot 60%, third shot 60%, and if you have to go the whole way to the 90th shot, your chances of getting that in the basket are 60%. So that probability of success is the same. Independent, constant probability, not too much different, is it? And the x, which will be a certain number, is how many times you have to do it until you get the first success. How many times do you have to shoot until you get the ball in the basket? And one thing to remember is that Q is just the complement of P. In other words, the probability of a failure is 1 minus the probability of success. Now I'm going to make a slight change to this one, and I'm going to explain why I would write this a little bit differently. Because first of all, if you think of it in terms of shooting a basket, for example, or hitting a golf ball, you're going to keep doing it until you get it in the hole or in the basket. So to me, these failures come first. X minus 1 of those failures, and then the success. Now this looks nice. This one is more chronological. It's up to you which you want to use. I just made up this one on my own, just because I like things in a nice, orderly fashion. So here's an example. We're going to use the geometric distribution this time. We'll get to the Poisson in short order. We found that the failure rate of businesses after 5 years is 50%. So we can write this down to begin with. We know we're going to need that. And 5 years ago is just something we're sticking with. It's part of the question. We're selecting them at random, and we want the probability that the fourth business selected is the one to fail. So in other words, the first one doesn't fail. The second one doesn't fail. The third one doesn't fail. The fourth one fails. And on each one of those, the chances on this one is 0.5, 0.5, 0.5, and still the same on the fourth one. So how do we work that one? Using those numbers, remember, Q is 1 minus P, so Q is 1 minus 0.5, which gives it the same probability, but that's how you calculate it. So you're going to take the 0.5, this is the probability of success, and since you find one on the fourth try, 3 times businesses didn't fail, and then the last one failed. And there's the simple calculation. But if you want to do it a little bit easier, we have a TI-84 solution for that. Now notice we have PDF, so that means we're talking about exact. And in this case, our first one that fails is on the fourth one, exactly 4. That's why we use the PDF. And the way we do it is we put the probability first, which in this case is 0.5, and we're talking about it happening on the fourth try. So there's our setup. Go to second, bars, which takes you to the distribution menu, and you go down to the bottom. In fact, the way I do it is I hit the up arrow, which takes me to the bottom of the list, and then I go up to GEOMET for geometric, PDF, P because we're talking about exactly 4 until you get the failure. And then you'll put in the numbers. In this case, 0.5 for the probability of failure in this case. It sounds sort of backwards, but I hope you get what I mean. And X, we want it to happen on the fourth try. So your calculator should look like this when you hit enter, and there is your probability that the first business failure is on the fourth business that you select. And let me clear that for you. Here we go. Where am I? There we go. There. That looks a little bit better. So here's our probability. So the probability that the fourth business selected is the first one to have failed is about 6% or 6.3%, depending on where you decide to take the decimal places. Now, that's the geometric. We're going to move on to the Poisson distribution. And this one's different. In some ways, quite a bit different, but it's easy, maybe even easier to solve. First of all, it's another discrete probability distribution. We're still in chapter 4. And here are the conditions. We're going to count the number of times this happens in some kind of interval. Now, an interval is very general. It might be per hour, for example. How many times does something happen in an hour? Or maybe per month. For example, how many times a month does it rain in South Carolina in June? The interval can be an interval of time, area, volume. The more examples you actually try, the more exercise you do, the more you'll get the feel for the Poisson distribution. The probability, as the other ones, is the same for every interval. Remember, Poisson, we're talking about some kind of interval, time, area, or volume. And the number of occurrences in any one of those intervals is independent of any other intervals. All right, conditions continued. A little bit more. Well, actually, it's not a condition. This is how we calculate that probability. And you can do this on your calculator directly. It's not really that hard. The mu here, you know, mu represents mean. That's the average. X represents how many occurrences you're interested in. E is what should be your old friend Euler's constant, 2.718, etc. And this minus mu is the same mu that we put right here. And down here, this x factorial, we've talked about factorials before, and this x is the same as the x that you found up here. Let me clear that for you so it's not quite so messy. So there's your formula. However, you might choose, like I would, to use the TI-84 calculator. And again, you go to second, vars. That takes us to the distribution menu. It's this Poisson distribution is toward the end. Well, not at the end. Near the end. So here's an example for us to play with. The mean number of accidents per month at a certain intersection is 3. So let's start our list here. So the mean is 3 accidents per month. Month is the interval. The interval that we're talking about for the Poisson distribution. In this case, we're talking about a month or a time interval of a month. Now, what we're interested in is the probability that there are exactly 4 accidents at that intersection. So we've got mu equals 3. The x that we're interested in is 4 accidents. And all we need to do is use either our formula, if you like, or you can use your TI-84. There's the formula. Remember, this is mu, this is x, there's E, Euler's constant, there's minus mu, don't forget the minus, and down here we have x factorial, in this case 4 factorial. Do that in the calculator, and if you want to do it that way, you should get about 16.8%. Or use the TI-84 like I do. The average goes first, or the mean, and the number we're interested in goes second. And in most of your calculators, it asks you by mu and x, so you know which to put in where. And that's how it should look on your calculator. You're going to go to the distribution menu, pick out Poisson PDF, because you're talking about exactly 4 accidents, and your calculator does the rest. 0.168 and so on. Let's try that one more time, just a little bit different. This time, the average number of rabbits per acre. Now this time the interval is an area, an acre. So the average number of rabbits per acre is 3.6. We're given that historically, perhaps. And we want the probability that there are 7 rabbits found. That means our x is a 7, and we're talking about exactly 7 rabbits. So we're going to use Poisson PDF, and using the TI-84, which I expect you to use. There's our result, second vars, which is the distribution menu. Go down to Poisson PDF, don't forget, because we're talking about exactly 7, and let the calculator do the rest. The probability is a little bit over 4%. Well, that's it, folks. I hope you found this easy, and I hope you find it fun playing with a couple of those discrete probability distributions. Don't forget about the binomial. So you want to know the binomial, you want to know the geometric, and the Poisson. Not too many to learn. Each one of them has a condition, and it's done a different way, but each one of them you probably want to use the calculator. Well, until next time, keep smiling and take care. Bye.